Now let's see the validity condition of WKB approximation. So here we already derived the functional form of or the functional form of our solution is psi of x equal to some amplitude multiplied with some e raised to I by h cross s of x kind of function, and for the moment I am taking this amplitude as 1. It's a unit amplitude, so I just have to follow what is happening with the functional variable. Okay, so I'm taking this function and putting it in my expression, Schrodinger equation. So my Schrodinger equation is nothing but d square by dx square psi of x plus what else? I modified that into p square x divided by h cross square psi of x equal to 0. So we have to find this quantity. D psi by dx is going to be nothing but you will be having an s prime I by h cross s prime, and this same quantity raised to I by h cross s of x, and when you are taking d square psi by dx square, you have two functions here. So the first function will be 1 by h cross s double prime, this quantity, plus another one will be again differentiating this term, which will again produce this I by h cross. It will become I by h cross square, and s prime is there, again one more s prime will come, it will become s prime square, and the same term repeats, which is common for both the term and also common for this term. So commonly it will go into the RSS and will become 0. So the expression will be something like okay, I will directly multiply. I know this term is minus and I just want it to be positive, so I am just multiplying this Schrodinger equation, entire equation means this plus this equal to 0. Okay, so Schrodinger equation will be nothing but 0, that term whatever is there, and you're putting that p square by h cross square equal to 0. So I'm multiplying the entire equation with minus h cross square, which will give you something like s prime square, it become positive now, minus p square minus this will become ih cross s double prime equal to 0. So this is a kind of an expression that I am obtaining. And now what happened here? So one thing we know about this WKB approximation is that it's being motivated from the classical physics, and it's valid. It's kind of valid for all the classical system. So when we are trying to put this for a classical system, it has to be valid. And how this is going to behave in the case of a classical system? So what happened when you're putting, or what is the connection when you have between classical mechanics and quantum mechanics? So one way of connecting them is like the finiteness of h cross value or h value, Planck's constant. So in quantum mechanics this is going to be a finite value, but classical mechanics it's kind of an approximation that it is going to, it's a limiting case when h cross tends to 0. So quantum mechanics at the condition when h cross tends to 0 has to lead to classical mechanic kind of a system. So in this expression, if you're seeing for a classical system, if you're applying, you know, this quantity ih cross s double prime is going to be really small, because this h cross is really negligible in the case of classical systems. Now if we want to apply the same scenario for a quantum mechanical system, naturally we have to ensure that this entire term is going to be, it has to tends to 0, the same way that it behaves for classical systems. So that is going to be our condition. So the entire thing is being motivated by classical uh, picture. That's why the name semi-classical formula came. Okay, so how do we make sure that this term is going to be zero in quantum systems? Because quantum system, you cannot really say that h cross is really very small, but to make the entire term small, you can take that the s double prime, when s double prime is really small, the entire term is again going to be small. So the condition that we have is something like s prime. If you're taking your s prime is another variable over here, compared to this term, this quantity is going to be really small. That is the condition that we want for the validity of this approximation scheme. Okay, so that will give you something like, yeah, s prime, this is having no, okay, s prime square is going to be really large compared to my I. Okay, just take the magnitude of it, h cross s double prime. So this is a condition when it is getting valid. Or if you just take the magnitude in the form, I just take here also magnitude, and putting that expression s prime square in the RHS, it will become something like mod h cross s double prime divided by s prime is going to be really small than 1. And I can rewrite this expression slightly. This is s prime square. I can rewrite this expression in this form. It is h cross d by dx of 1 by s prime. So what happens here? When you're taking the derivative of 1 by s prime, it is nothing but minus 1 by s prime square, and s prime d by dx of s prime, which will give you s double prime. So that is a minus sign will be there, but it's mod minus 1. Or what about this s prime? That s prime is nothing but your p. See, in this condition we already have derived it s prime. Okay, if you just compare the real and imaginary parts separately, you just obtained s prime equal to p. So s prime is nothing but your p, and you have a constant here. There is nothing wrong in taking s prime s cross inside. So what you have inside of d by dx is d by dx of h cross divided by p. It's a momentum value. H cross by p is h by p, you know. H by p is nothing but lambda, our de Broglie wavelength. Of course, in this case of a slowly varying potential, we can take a variable dependence on x. So here again we have x dependence, but h by p give you de Broglie wavelength, and h cross by p we call that as lambda bar, de Broglie wavelength, but divided by 2 by factor. So this is going to be nothing but d by dx of h cross by s prime, which will be something like lambda prime, lambda bar. It is equivalent to your lambda, only thing is divided with a 2 by factor. So this is a condition that we obtain for the validity of this approximation scheme, that d by dx of lambda bar is really small, smaller than 1, or it is nothing but the rate of change of lambda, rate of change of de Broglie wavelength, change of de Broglie wavelength with the variable x with the distance has to be small. When the rate of change of de Broglie wavelength with the distance is small, you can indeed apply this approximation scheme.